It's a pleasure to have Rome Samantha from INFN Naples and SSM. Rome got his PhD at SINP, working with Prabir and Amber Ghoshal, you said?
Yep. Yep.
And then he moved to Southampton for his PhD postdoc, and then to Prague,
Yes.
and now he's at INFN. So please.
Yeah. Okay. So, can you? Is it audible? Okay. First of all, thank you very much for giving me this opportunity once again to speak at IMSC, and this is my kind of first time at IMSC. So, and also I had the opportunity to interact with some of the faculty members, which was a very nice interaction. And I would specifically like to thank Sri Hari for arranging this visit and also paying for my meals for the time being. Okay, so as you can see from the title of my talk, that I'm going to talk about leptogenesis and its connection with the gravitational waves. So leptogenesis is a process with which you can generate the Baryon asymmetry of the universe, right? So although I chose to speak on leptogenesis, but my main motivation for this talk, or to present this talk, is to promote this research area where you study beyond the standard model of particle physics. It may not necessarily be leptogenesis. It could be dark matter, it could be axions, it could be leptoquark or whatever, and you study those theories with gravitational waves. Okay, so or in general, I would like to promote that early universe cosmology, probing early universe cosmology with gravitational waves and their future prospects. And I'll give this talk with leptogenesis as an example. Okay, so before, okay, I did my talk is based on these two papers basically, and also with I did this work with these guys, and yeah, so before I start my talk, let me give you a disclaimer that this field of research, which is a very small subset of probing BSN theories with gravitational waves, connecting leptogenesis is gravitational waves, is basically pretty new subject. Okay, so this started from these two papers. The first one was by Muram et al. In 2020s, and then a paper by me with a student, Shoto Broto. And now people are working on this particular field. It's more, and now it's more than like 70 to 80 papers. I keep count on the papers because I become happy as I get citations with in this field. Okay, so but the point is, in most cases, whenever you do a BSM theory, uh, when you try to find signatures or gravitational wave signatures, in most cases the signals are not smoking gun. Okay, so meaning if you observe a signal, it is actually honestly difficult to say whether it's coming from this leptogenesis model or any other models. You can reproduce it with various different kind of models, but the primary motivation of this kind of research is the bottom up view, meaning if you don't observe that signal, a significant part of the parameter space will be ruled out with gravitational wave, with the gravitational waves experiments. So this is basically the idea, because there is no other way you can touch that parameter space with any other experiment. Okay, and having said this, let me start my presentation. That I have a few slides, like very formal slides on the context and motivation, and then I'll try to introduce the core idea of how to connect leptogenesis with gravitational waves. So I kind of have two segments. In the first segments, I will formally introduce, I mean, many of you know actually what is leptogenesis, but what people have done so far, like to test leptogenesis with particle physics experiment, in particular focusing on neutrinos. And then why there is a slight shift of paradigm, that people are now trying to connect it to the gravitational waves because of the of lots of opportunities. Okay, and then in the segment two is basically I have two slides. So in the first slide, I would like to I'd like to tell you one of, I mean, some loopholes of my work, and then uh, I'll speak briefly about how to do forecast analysis with gravitational waves experiment. For example, taking LISA and as an example. Okay, so LISA is still not launched yet. So whenever I say forecasting, so it's meaning a mock data analysis. Okay, so yeah, so Then I'll conclude my talk. Okay, so why early universe gravitational waves? Once again, because gravitational waves are very weakly interacting. So if you have a theory at very early universe, they can carry very pure information, like information without any distortion, and therefore you can probe energy scales up to 10 to the minus 35 seconds, like after the I mean it's very deep into the early universe. Okay, so this is a kind of standard picture of early universe, and in general, what we consider there was a period of inflation. Then we have radiation domination, and also then we have matter, then dark energy. So what we know that during BBN there should be radiation, and before that the equation of state is kind of unknown. So there could be any other equation of state. And in my talk, this equation of state is going to be a very crucial part. And because gravitational waves are very sensitive to this equation of state, and therefore, if you change the equation of state, and what you get in the standard case, like standard cosmology, the spectrum of gravitational waves will be very different. And if you can build a model in a way that in your model you are like playing with equation of state, so your imprint of your model will be seen in the gravitational wave spectrum. Okay, and regarding the experimental motivation, I think the experimental motivation is much more stronger after 2019, when pulsar timing arrays they released their data, and they claimed that they found evidence for stochastic gravitational waves background. So I'm going to talk a bit about pulsar timing arrays later in this talk, but just to tell you, pulsar timing array operates in the frequency range, which is like nanohertz, 10 to the minus 9 hertz. The interesting fact is within this range, which is nanohertz, the most natural source of gravitational waves is astro source, which is supermassive black holes. Okay, but surprisingly, when the pulsar timing arrays, including the Indian pulsar timing array, they released their new data in 2020. Uh, the data showed something different, and people studied like the different cosmological models and compared it with astrophysical models like supermassive black holes, and they found that many cosmological models actually do better than the supermassive black holes. So for example, with this plot, so this is a curve called Hellingsson-Downs curve. I'll explain it later. So if you find this curve in the data, that means your data is basically your data has stochastic gravitational waves background. Okay, and this plot is a comparison plot for astro sources with cosmological sources, and base factor is basically a statistical quantity where you compare the Bayesian evidence of two models, like model A by model B, where model A is the cosmological models and model B is the baseline models, which is supermassive black holes. And if the base factor is more than one, then the model is doing better than the model B. Okay, and kind of, yes. I mean, it's coming from unresolved sources. So you cannot really resolve the sources, yes. But what I'm going to say is zeroth order gravitational waves, which means I'm going to say isotropic gravitational waves. I'm not going to say anything about the anisotropy of gravitational waves. But
Then why call them stochastic instead of thermal gravitational wave?
Because it's coming from in random directions. That's why, like stochasticity.
See, everywhere also it's coming from all directions. Right?
Okay. Oh, no, no, I mean, same photon thermalizes, but gravitational wave do not have that interaction strength to thermalize. So it's not a thermal gravitational waves. Okay, so yeah, this was the experimental motivation. So not only pulsar timing arrays, as you can see that there are many other detectors operating at different frequencies. So pulsar timing arrays operate in the sky. There are like planned detectors like LISA and DAISYGO, and also ground-based detectors like LIGO, Cosmic Explorer, and all these things. So this means that if you have a spectrum, like extended spectrum from your theory, where on the horizontal axis I have frequency, and where on the vertical axis I have energy density. So this is a normalized energy density, and the definition is like this. This means that if you have a theory which has an extended spectrum, you can test your theory with a multiple detector and do a multi-frequency gravitational wave astronomy. Okay, and that's why possibly this subject is getting popular. So yeah, so after the release of pulsar timing array data, now like main gravitational waves detectors like collaborations like LISA, Einstein telescopes, they already publishing their cosmology or BSM physics pipeline, and like which kind of BSM models they are going to explore in their upcoming missions. And LISA just has been approved. I think it will be launched somewhere in the middle of 2030s, like 2035 or around. And but I think Einstein telescope would take some time to be operating. Okay.
Going back to Sanatan.
Okay.
So why do they lose the directionality to the source if they're
No,
not interacting? Then
no, because sorry,
why do they lose the directionality to the source?
because in our universe the sources, I mean, it's are randomly spread. Like it's
So it is an extended source that produced them.
That's
the way to think about it.
Yes, not extended. I would say
they could have
extended emission. Like for example, you
Sorry, in your case, it is something else. But black holes also could lead to stochastic gravitational waves, right?
Yes.
Black hole.
Yes.
Then why do they lose the directionality to the thing?
Because if it is astropically
distributed
with the power spectrum that is coming from the early universe, let's say some power law or something like that. So directionality you cannot find, but you can find their power spectrum.
Now, why not directionality?
Because you can.
It should point to some source. But there could be
individually, how you are seeing a bed of like a ripples, but you can say that yes, that is my source, but it is just a ripple that you are seeing. No?
Yeah.
And you are seeing something in a frequency spectrum.
Because there are many sources, right?
Because there
are many sources,
overlapping sources, and that's why you. All right.
Okay, so yeah, so these are my notation, but the crucial equation for this talk is this one, which is the gravitational waves generation equation. These are the tensor perturbations. These H, capital H, the Hubble Hubble parameter, and the most crucial quantity is on the right hand side, which is called anisotropic stress, with which you generate gravitational waves. So whenever you do an early universe physics, you basically need to compute this anisotropic stress in your model. And that's how you generate gravitational waves and plot that, plot this. I mean the previous frequency spectrum. Okay.
Then the Hubble, the expansion rate.
Yeah, I mean you need to basically solve this equation in two limits. One is sub horizon limit and one is super horizon limit. So you need to take. I mean, if the wavelength is more than the Hubble inverse of Hubble, then it's the super horizon limit. Then you solve this equation and like find the super horizon spectrum, and then you solve the in different limit, which is sub horizon limit here.
That's one of the.
Yes.
That should be valid, no? Because you are solving it.
This
nonlinear terms coming from
games. No, I think that you were talking about the second order term, no?
Because it's a linearized theory.
Yeah.
For example, when we talk about scalar perturbation, it is of the order of 10 to the power minus 5. So we have seen CMB fluctuation of the order of 10 to the power minus 5. If it was of the order of 10 to the power minus 1 or nearly 1, then we could not have linearized it. If it's 10 to the power minus 5, then your perturbation theory is valid. But yes, in a very small scale where we do not know what happens, we do not have anything, then in those cases, if there is a scalar induced thing, you need to take into account.
But tensor perturbations are also not explained, right?
Yes, then at the very small scales, you have to.
This is for early universe, you got scales.
No, early universe also there is a large scale, so there is a small scale that you have to go. For example, you can be a meter scale and there can be gigaparsec scale corresponding. So in that case,
no, but I understood that this is within the Hubble radius.
This one is it's a generic equation, no?
It's
generic equation. It's not within the Hubble radius. So you need to solve it in two limits, and that's what I'm saying.
You have to solve it in two limits.
Two limits, yes.
So the source is some, like near field configuration or something.
If you take a particle physics model, for example, strings or domain walls, it could be like field configuration, movement of the field. So
what you're going to focus on?
Yes, I'm going to talk about strings and also a little bit about domain walls. So this pi ij is basically this related to the stress tensor like this, And within this stress tensor, you basically include your fields and all other things.
All right.
Okay, so once again, my talk is going to be dealing with phenomena which happened after inflation. Okay, so leptogenesis, how it works, basically, it's a simple process where you create lepton asymmetry, and with there's a process called Falloran. With then you convert this lepton to baryons, and this is how you generate a baryon asymmetry. So there are many channels or many possible ways you can create this lepton asymmetry. For example, if you have primordial black holes, you can have gravitational.
The equations I can't read.
Sorry about this. This one. Okay, so this one is basically baryon to antibaryon numbers normalized to. Okay, sorry. This is eta b. This is nb minus nb bar over photon number density, which is of the order of 10 to the minus 10. And this is observed baryon asymmetry. Okay. So yeah, and but the most popular mechanism is possibly you do with heavy neutrinos, because once you include heavy neutrinos, it also connects to neutrino physics. For example, you can have a Lagrangian like this, where on top of standard model you include these heavy neutrinos to generate a Majorana type mass term, and this is kind of a Dirac type mass term. And with this Lagrangian, you do a seesaw mechanism. So basically, with this seesaw, you get one state which is very light, and with that you explain light neutrino masses. And then with these heavy guys, there is one heavy state which basically decays to lepton and antileptons, and that is how you generate lepton asymmetry. Okay, so the process is like this: you have the heavy
0.01.
It's basically the Falloran conversion coefficient. Like
it's usually around 0.01.
Yes.
That's
Yes. Okay. So this is basically how you create lepton asymmetry. You have a heavy neutrinos which is decaying to lepton and standard model Higgs, and this decay is CP violating decay. Okay, meaning if you conjugate this process, the rate will be different, and once you subtract that, like the standard decay with minus its conjugate decay, you will get a parameter which is called CP asymmetry parameter, which would look like this. Okay, where these terms are proportional to like MD, which is the Dirac type mass matrix in the neutrino Lagrangian, and these Xij's are some combination of the heavy masses. Okay, so as you want to generate the baryon asymmetry from these heavy neutrinos, so there will be two basic equations, right? The first one is how you populate these heavy guys, which is the population equation, and the second one is the lepton asymmetry generation equation. The most crucial term in this equation is this washout term, which is this W. So there could be different washout interactions, but the main interaction is the inverse decay, because when it decays this way at high temperature, it can inversely decays to produce heavy neutrinos. Okay, and therefore they can wash a significant amount of baryon asymmetry. So once you solve this equation, you can have a plot like this, where this is how you populate the heavy neutrinos from the first one, and this is how you generate the baryon asymmetry from the second one. Okay, but the crucial thing is that when you are at z equals to 1, where z is m over t and m is the mass scale of the heavy neutrinos. I'll focus more on this m later. This freeze out thing happens around z equals to 1, meaning around the temperature which is of the order of mass of the heavy neutrinos from which you generate this asymmetry. Okay, and typically you call it the scale of leptogenesis. And people who work on this leptogenesis scenario, they want to probe this scale. For example, if you have this m to be of the order of GeV, EV, you can produce it in the collider, so you can have a collider test of leptogenesis. Okay, but if the process at if this process happens at super high energy scale, so there is basically no other ways to probe these scenarios. So people who are trying to connect these gravitational waves to this leptogenesis, they are basically trying to make this M sensitive to the gravitational wave spectrum. So that is basically the basic idea. Okay. No, this is not. I mean, these scattering and decays are is zero temperature cross section with thermal averaging. It's not the finite temperature. But if you can do a finite temperature correction, then I mean, this there will be some modification to this relation, like something 5 to 6% modification if you do a finite temperature field theory. Yes, but yes, that's something. Yes. So it's for if your mass is more than. Typically, people have studied this thermal correction for high scale leptogenesis, for which I think the scale is 10 to the 9 GeV, more than 10 to the 9 GeV. Yeah, for that.
Much more than that, because heating temperatures are typically of the order of.
No, it depends. Heating depends on which kind of inflation model you take. For example, if you have yes, yeah. So this is very crucial that you. I mean, it's thanks for commenting this. I skipped it. So I assume that reheating temperature is more than this scale, so that you can thermalize these heavy neutrinos and you do the process. But if the reheating temperature is less than the mass scale, then basically you cannot have thermal leptogenesis. So this is what I'm talking about is thermal leptogenesis. Okay, but if the mass scale is more than reheating, this mechanism is called non-thermal leptogenesis. You can also do this non-thermal leptogenesis, but in that case, you do not have this scattering interaction to produce heavy neutrinos. You need to have some other sources to produce these heavy guys. For example, people did it with black hole or inflaton, couple these things with inflatons and to produce this heavy neutron. No. Typically, this is the CP violating parameter, and I'll also show how UPMNS is coming into this picture. Okay.
Why does NN1 take so long to thermalize?
It depends on which parameter. Okay, so this K parameter is basically a parameter which you derive from this neutron physics parameter, right?
Yeah.
And this is for K equals to 100. If you take more than K equals, K is okay. Let me.
So it should be whatever is the interaction strength, right?
It is basically related to interaction strength.
It should be related to the Yukawa coupling.
Yes. MD double.
So is this like a very small Yukawa coupling or what? In that limit, it takes this long, or generically?
Yeah, this K, if you have K equals to 100, typically you have a small Yukawa coupling.
No, if I have a Yukawa coupling of order 1, then it should not be like this, right?
No, it should thermalize very quickly. I mean,
yes,
it will be.
Why are we assuming a small Yukawa coupling here?
No, it's just for example.
This is just some represent.
Yeah.
There could be other.
Yeah. I mean, in realistic scenario, when you feed the neutrino data, for example, you need to scan over all the parameter space.
Okay. And why that? That
dip in the middle. So it's basically I plotted the absolute value. It's basically sign change in this.
Okay.
So the leading order corrections due to finite temperature, could you tell what is the behavior like? Is it proportional to what
actually,
power of temperature?
I mean, you are talking about the CP asymmetry, finite temperature correction to the CP asymmetry parameter or to the scattering proportion? Like how?
Like you just said that the mass, some 5 to 6% correction.
And the 5 to 6% correction to this scale, but I actually forgot what is the whether it's like power law dependence on aim or I don't remember it at this moment. Yes. Maybe I can tell you later. I just need to see the reference. Yeah. So yeah, I mean, this is basically A and B minus. I mean, how you calculate? So this is with this equation, you can compute this B minus L, and then you want to compute B. So basically, when you relate this B equation to the B minus L, then the Sphaleron coefficient will come. The Sphaleron is already operating, so I'm not considering Sphaleron in this equation. Yes, Sphaleron rate depends on temperature. Yes, it's basically. For what?
Parallel process. Above surface.
No, so whenever I'm talking about leptogenesis, that means you are converting lepton asymmetry to baryon asymmetry. You need to be above the electroweak scale because the freeze out temperature. I'm talking about electroweak sphalerun. Freeze out temperature below which sphalerun you can collect sphalerun is basically 130 GeV or something like that. Yes. So,
If you do it above electrode scale, then the washout might be significant.
no, it depends on this parameter. So this K parameter, I'll talk more about that washout. Yeah, I mean, there are different regimes like strong washout, weak washout, and all these things. Yeah, but I think you are talking about washout with sphalerun, by sphalerun. No, that happens only in gut baryogenesis, not leptogenesis, because in the gut baryogenesis you typically conserve B minus L, and sphalerun conserves B minus L. So therefore, whenever sphalerun is seeing an interaction which has B minus L conserved, it try to pull the system again to the B minus L. So that is the sphalerun washout. But in this case, you already have lepton number violation. So you already have some violated lepton number. So basically the sphalerun will redistribute the asymmetry to B and L. So it's very opposite scenario to the gut baryogenesis. So in this case, sphalerun just convert lepton asymmetry to baryon asymmetry with some efficiency factor, whereas for the gut baryogenesis, sphalerun is basically the antagonist. It basically washes everything. Yeah. So
Sorry. Gut baryogenesis, you're saying B minus L is conserved throughout, right? Is that
so sphalerun conserves B minus L,
Yeah.
and whenever you do like some models of gut baryogenesis, you have B minus L conserves. Yeah.
Exactly.
Yeah. I mean, of course, there could be some models where you do not have these conservations. Yeah.
Have that, then you're saying it will wash out.
It will wash. It will. Sphalerun is going to wash out. That's the problem of the standard gut baryogenesis. Yes.
Yes. Sorry, why does it work? It conserves B minus L.
It conserves B minus L, but sphalerun also conserves B minus L. Sphalerun individually violate B.
Yeah, why
delta
should
B
it
and
be washed out if it is conserving?
no, because B.
Maybe we'll talk later.
Yeah, sure.
Yeah.
Sure. Okay. Okay. So generally, so in neutrino scenarios, you generally include 3 heavy neutrinos because I mean 2 heavy neutrinos are okay to explain neutrino oscillation data, but in principle you can start with 3 heavy neutrinos. Okay. So generally these heavy neutrinos can also produce asymmetry, but these asymmetries get washed out by this N1 interaction, and what survives, that only the asymmetry you produce from the lightest particle that survives, which is basically the N1 dominated scenario. And you can solve this system with this kind of equations, and you can see that, for example, take 2 neutrinos. This black curve is from what produced from N2, or the heaviest one, and the second one is the red one. Forget about the blue one right now. The red one is N1. So as you can see, the black one is like you get a significantly lower values. So so basically you include this exclude this N2 scenario in the standard case. But actually there is another effect that you need to consider. I mean, what?
Y-axis.
Okay, y-axis. So I didn't put anything, but let me tell you. This one is the like the lepton asymmetry that you get from different neutrinos. The black one is N2, and this red one is from N1, and these are the inverse decay rate for the red one is for N1, and the blue and the green one, blue one is for N2. So because I plot different quantities, I didn't put the level, but actually there is.
What should I?
So in this plot, you should focus on this black curve, which is the asymmetry produced by the heaviest neutrinos, and the red one is the asymmetry produced by lightest neutrinos. And what you get in the standard scenario, by standard, I will explain why I'm calling it standard, that you will have more asymmetries for the same parameter space from the lightest neutrinos. And whenever people study leptogenesis, they generally mean that they consider the lightest heavy neutrinos to explain the baryon asymmetry of the universe, because from the heaviest you get suppressed amount of baryon asymmetry. Because okay, so this blue is the inverse decay rate or the washout process effect for N2, and this red is for N1. And because this red is here, this basically is washes out by the asymmetry by the heaviest neutrinos. So whenever you generate asymmetry from the heaviest neutrinos, it faces wash out from the lightest one. So that's the problem of this kind of scenarios. Okay, so but there is another effect that you can cure this system. And also the same effect is responsible to connect the leptogenesis scenarios with neutrino physics. And this is what I'm going to tell what people were doing so far. And then I would like to go to the gravitational waves. Okay. So when the neutrinos are produced in the early universe, they're basically produced coherently, right? And because you have lepton doublet, they basically have also interaction with charge lepton, and therefore at some point the charge lepton interaction will be dominating, and they are going to break the coherence of the state, and therefore before it inverse decays, the coherence of this lepton state is already broken. Therefore, in the washout processes, only flavor guys will like inversely decays to heavy neutrinos. Okay, for example, this was initially this was a coherent state, but now, for example, if the tau lepton interaction is switched on, then it will be L tau, which is generating the heavy neutrinos. Okay, so and
State what? I mean, we are talking in the early universe.
in the early universe, yes. These lepton are states with, because it has a like coupling with all the flavors. So basically,
So you're looking at a decay of, right?
it's a decay.
Yeah.
Decay, production of this L state, which is the
Right.
doublet, which
Yeah.
will be coherently produced like flavor blind production actually. So in the early universe, you initially will have flavor blind production until you touch the flavor. And why you get you basically touch the flavor, because this lepton doublet also have interaction with charge leptons.
Right.
And when charge lepton, like, because the way you generate electron or tau or muon mass term, and when this lepton doublet start to see the charge leptons, then basically the coherent state gets broken. For example, when it sees the tau, then it will be broken to E plus mu plus tau. So there will be two states. And this is basically called the flavor effect in the leptogenesis. So an immediate consequence of this flavor effect that you reduce the washout term. Okay. And
So you were in a, if I think of them as mass eigenstates,
yes.
so we are talking about neutrinos or charged leptons? Neutrinos, right?
No, this one is the doublet.
When you talk about coherent and all that, are you talking about a charged lepton or the
It's a doublet. In the doublet, you have both.
Both.
Yes.
So both will be.
Yes, but
coherent.
when yes, both will be coherent. But when you have
But loss of coherence is for the neutrino or for the charged lepton?
loss
Charged
of
lepton
coherence,
anyway would be lost, right?
I
they
mean,
will interact.
loss of coherence is because of the interaction with the right-handed part of the charge lepton. For example, ER or tau R or something.
So
like
they will interact very quickly.
Yes. So
The neutrinos is what you will focus on for coherence or what?
for neutrinos, it's not. I mean, once you break
So what's the point anyway? What is coherence for? And
coherence, I mean, when the charge lepton is interacting, then basically this inverse decay, I mean, this lepton state is not coherent anymore. So this inverse decay will happen in two like with L tau and Le plus mu. So basically, you need to put the flavor index here now.
yes, and sum over that.
Yes, then sum over that. Yeah.
So it should be the same whether it is coherent.
No. So when you solve, because now you need to solve this equation like separately, then you sum over.
So it'll have a big effect over.
Yes. That's what I'm going to say. That once you include this flavor effect, then you reduce this W or washout term. So it gets significantly reduced. And secondly, because of the flavor effect, you make leptogenesis sensitive to the neutrino parameters. Otherwise, it is not possible. Okay. So
why is there such a significant effect?
Yeah. So let me show you. So yeah. So when you take the flavor effect, so you need to multiply these equations with this probability. For example, if you're computing the asymmetry in the electron flavor, you need to multiply with P1A And as if you go from this side to this side, so P1E basically, you have more concentrated values of P1E around 0. That means in the electron flavor, the washout is completely negligible. Okay. And similarly, you can compute the washouts in muon and tau flavor. So with that, what I mean that you can reduce the washout effect, and it will be very significant for N2 leptogenesis scenarios. Okay, and thus, okay, so this this probability parameter depends on the neutrino parameters like this. If you do not have a flavor effect, then you only have this K1. See, this W is proportional to this K1. But if you have flavor effect, you need to replace this K1 with this K1 alpha, and that's why this reduction. Okay, and one more. So let me skip this plot. It's the same plot basically. And one more thing, what happens? Yeah. So as I was saying previously, that you can neglect the N2 stuff if you don't include the flavor effect. So you can semi-analytically represent the leptogenesis scenario in terms of efficiency factor. So when you have N2, I mean, this K2 is basically the efficiency of the N2 leptogenesis. And when you do not include this flavor effect, this K1 is in general very large. Therefore, this you can neglect the N2 contribution as well I was mentioning previously. But once you include the flavor effect, then this K1 get reduced, and you can also have like N2 leptogenesis scenario in addition to N1. Okay, so what happens once you include flavor effect, that you have you can produce lepton asymmetry from N2, and then you create flavor holes at the scale of N1, because N1 washout was the main antagonist that was that was basically blocking the N2 leptogenesis scenario, and then you can generate this observed baryon asymmetry. Okay, so typically, so this was the case of washout, and what flavor effect does. So this is the CP asymmetry parameter individual flavor, and if you don't have a flavor effect, you sum over the CP asymmetry parameter. Okay, and you can show after parameterizing this MD like this, where U is the UPMNS, which basically enters in this equation. So this CP asymmetry parameter is basically independent of this UPMNS. So there is, if you don't include flavor effect, there is no way you can connect neutrino physics to leptogenesis scenario. So it's basically blind to neutrino physics. Okay, so flavor effect is very crucial. Okay, so and what people did, there are lots of parameters you need to consider to further constrain your theories. What people did, people included different kind of flavor symmetries so far to probe leptogenesis with neutrino parameters. For example, you can do like GART-based models, in which case to produce correct baryon asymmetry, you can have predictions on these neutrino observables. For example, this is theta 1, 3. This is delta, which is CP violating phase. So this delta is basically what is there in the UPMNS matrix. Okay, it is always not. I mean, it is not obvious that the CP violation in the UPMNS will be responsible for leptogenesis. It's not always because there are other CP violating parameter. So this delta gets connected to leptogenesis, or leptogenesis is seeded only by CP violation in the neutrino sector in special cases, basically. Okay, but not always. So you can get some predictions like this, and also you can get some prediction on the mass scale. So this is how so far people were trying to. So I'm just giving one example, but this is how so far people were trying to probe leptogenesis scenarios with flavor effect, with imposing more symmetries, including these models in gut-based scenarios where you can constrain your like mass matrices and all these things, and to compare it with neutron oscillation data, or give some predictions of the neutron oscillation data from leptogenesis, and how this is how you are probing leptogenesis so far. So now there is a paradigm shift. I mean, lots of people who are working on leptogenesis, they are trying to connect the leptogenesis to the gravitational waves. Let me give you a motivation from the pulsar timing arrays. So, now there are lots of experiments which are trying to measure the gravitational waves. So this is basically an experiment called International Pulsar Timing Arrays, which is a collection of radio telescopes which are operating and at a frequency nanohertz, as I was explaining. And Okay, so what these pulsar guys are doing, so I'm not an expert in pulsar, so what I know from the pulsar physics is the following. So they are basically monitoring millisecond pulses, okay, and they're measuring the pulses. And these neutron stars are very, super precise astrophysical clocks, meaning you know exactly from the pulsar catalogs, you know exactly when, if you measure one pulse, you know exactly when the next pulse to get, okay. But if there is an anomaly in the time of arrival of the pulses, for example, this was the expected time, that you are expecting a pulse, but actually it's coming, a little delayed, a little bit earlier way, then something is happening between Earth and pulsar system, right? So it could be some noises, it could also be gravitational waves. But if it's a gravitational waves, which is stochastic, there is a particular pattern that you will see. So this pattern, so this is basically a frequency which is related to time of arrival of the pulses, which depends on the gravitational. Let's say you have gravitational waves. This is the of the gravitational waves or strain of the gravitational waves, and this is the noise for the individual pulsars. So when you correlate these pulsars, okay, or correlate the time residual of the pulsars, if it's a gravitational waves, you will get this curve, which is called Hellings and Downs curves. And this is very exclusive to the stochastic gravitational waves. You cannot reproduce it with any other means. And so the analytical expression for this is like this. I mean, you plot this curve with angular separation in the sky with the correlation strength, you'll get this curve. So now if you have a data, for example, and this data show the evidence of this curve, then basically you can say that there is some stochastic processes, which could be astrophysical, which could be cosmological as well. Okay, and if you look at the data, so basically this
stochastic gravitational waves, they have some characteristic, like how do you mix the different modes and so on. There's like a specific
this is
way.
okay. So this is for the tensor mode. Yes, this is. I mean, you compute this integral.
What frequencies or k values or all that are going in there with what amplitudes? What about that information?
I mean, from this, how you compute?
Not how you compute. What is the nature of the stochastic gravitational waves? It can be characterized by some power, right? And as a function of.
I mean, okay. So you mean what
As a function of
what
L.
pulsar timing array data found? Like which is the like which
I'm
power
saying
law they
is,
found?
does this curve
Okay.
depend on
No,
the
it basically doesn't depend on the frequency spectrum of
yeah,
the
how come? No, why not? It should,
actually.
no?
mm, Actually, I don't remember at this moment how
Okay.
it's
Yeah.
here. Yeah, but what they found in the data that the frequency spectrum is f square basically in the pulsar timing
Is-
data, f square, f to
F
the
square.
f to the 2 quadratic.
Stochastic gravitational waves always must have F square.
No, what pulsar timing array found that they found an f square. It could be anything, f to the 2, f to the 4, depending on the model.
Then it should be sensitive. Something must be sensitive.
I mean, I'm not sure whether this pattern in the sky is sensitive to any power law of the gravitational waves. So,
What are there is some other observation that they have other than this correlation?
no, of course you have the amplitude and frequencies for sure. Okay, so this is what they found in the data. So this is for nanogram.
What? I mean, you're not detecting the gravitational wave, or are you? This is from pulsar time.
This is from pulsar timing array.
There you don't have anything else other than the correlation.
No, I mean, you also have energy density of the gravitational waves per frequencies, right? Like they have like in individual frequency bin. I mean, pulsar timing arrays are operating at the nanohertz frequency. So basically, it depends on what is the distance between Earth and pulsar. So once you compute, like when you think in terms of frequencies, so basically you can have this curve only.
That is independently you do not get there. From this one you can reverse engineer there. That's what here is asking.
Meaning in knowing like how far individual pulsar is.
Yeah, I mean, I think it's the only thing that you get from PTA. You do not.
Is that the only thing? That's the question. Is this the only thing, or do you get more?
I think you also get for I mean, what they reported is the like F square power law, like for individual frequency
They tell
beam.
you which individual pulsars went into where and all that. You know,
No,
right?
no.
It just said you just have this one.
Yes. But to be honest, I really forgot how to like get this frequency versus energy width from this curve. I don't recall this right now. Yeah. Okay, so this one was the data, and therefore, if you have like a theory which has like some signal at the nanohertz, you can fit the pulsar timing array data. So what pulsar timing arrays are operating in this frequency regime, which is nanohertz. If you have
The points are
so this so look, this EPTA data is kind of crazy, but so that's why it's not very firm. That is a gravitational wave. So what I mean, this curve is a theoretical prediction. If you take the tensor modes, if you take like alternative theories of gravity, you can have like different modes, like Uh, scalar modes and also vector modes, in which case you can have like pattern like this or some different kind of pattern. Okay, and people who are working on modified theories of gravity, they are also writing this in the paper in a way that their curve can also fit the data. So as you said, this data is kind of scattered, but people who are optimistic that this is actually the GR gravitational waves, they're saying that this is, I mean, if you take more data, this will follow the GR curve. Okay. Yeah. So this is the analytical prediction, this black one. That I don't know whether they try to fit like whether they try to fit. I mean, this Hellingsdown curve has a free fit, whether they try to fit it or not.
Yes. Yeah. New. This is EPTA new data, right? There is hardly signal, isn't it?
Yeah, so I think EPT did a combined data analysis with Indian pulsar timing arrays. So I think these browns are from EPT and these greens are from Indian pulsar timing arrays.
Blue ones.
Yes.
But actually, if you combine this data, it seems that there is no signal.
No. For EPTA, some people. I mean, when people are writing paper, they are only focusing on nanogram because yes.
Orange shows something.
Yeah, orange one shows something. Yeah.
Orange are systematically lower. It shows something. Yeah. But if you look at the blue ones, what is orange and what is blue? Two different data.
Two different data. So it's combining data with iron Betty. Yes.
Oh, Indian.
Yeah. Okay, so if you have a theory which is, I mean, you can also have like prediction somewhere like this, which is the Daisy-Go or Lisa, or you can even have the signal like LIGO, and in which, I mean, with which you can constrain your theory, right?
Differently, the curve can be modified or what, depending on your theory.
Yes, this curve is a GR curve. If you have a modified gravity theory, you can also generate this curve for other modes like scale.
It doesn't depend on the sources, nature of the source.
Yeah, so it's for tensor.
But what tensor, for example, it can scalar induced gravitational wave. It can be your theory that is that.
I mean, that's how. I mean, I think that's this one is. I mean, you were saying this Hellingsdown curve, whether it depends on the source of the gravitational waves or not. No, I don't think so.
So you say, can you go to the next?
Okay.
Yeah, so whatever, let us say I take one of the theory from down, let's say the bubble collisions and things like that, and I take it from the stochastic thing. Maybe there is one peak and there is an extended peak. That is falling in the pulsar timing, this nanohertz frequency regime. Won't it make any difference in that Hellingsdown curve?
I think if it will make difference only if you have a different amplitude, not the spectral shift. I mean, if you have like different amplitude, then it's basically I mean, the strain of this guy. Then basically you cannot see the.
No, from the third, from the
Mhm.
next slide,
This one.
from there,
Mhm.
when you go to the helix down,
Mhm.
if my theory changes here, keep GR. Let us say having GR is there,
Okay.
but from there to helix down conversion, only amplitude matters, not the profile of the omega GW power. This omega GW.
That's what I yes, I think yes.
Matters how?
I mean because you have this relation. I mean the amplitude is coming here.
Yeah, what will change in this curve? As you change the amplitude, what will change in the helix down curve?
I mean this is basically correlation strength, right? And this depends on delta mu.
Shape of the curve will change as you
No, I think you won't get any curve at all because if you let's say you have like zero amplitude, it's basically this
No, when
correlation.
you jack up the amplitude, what will happen?
Like if you like
Yeah,
increase.
if I make alpha I bigger, will this curve change?
Mm, 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 mm. I mean you mean the pattern of this guy scale.
Exactly like that, or will it change?
So I think you will get a trans. I mean, this is a coefficient. So there are other coefficients that will depend on the strength of this H, right? So this what I plotted here is a alpha Ij,
Yeah,
which is
alpha
independent.
change or not?
Alpha Ij won't change. The shape will remain same. So what you will have a translation either in this way or in upward way. That's what I'm saying. Okay, so so whenever you want to generate gravitational waves from early universe source, as I said, you need to generate this anisotropic stress. For example, if a simple example would be domain wall like scenarios. So I'm not going to the detail of this. Like this is a result from a simulation. I'm not going to the detail of the simulation, but in case if you're interested, you can see my talk, which is on the YouTube, like where I kind of try to explain how to do these things in lattice and all these things. So, so you need a source like this. Okay. Now let us come back to our leptogenesis Lagrangian. So the full Lagrangian for leptogenesis would be like this, where this term is related to the Dirac mass term. This is the Majorana mass term, and this is the self-interaction coupling of standard model Higgs with the new field, which is giving you the Majorana mass term. Okay, and this term is quite crucial, where this V phi, this V phi t, which is basically the finite temperature potential of this scalar field. Okay, so in principle, given this Lagrangian, and depending on how you construct your theories with different kind of symmetries, in principle, you can have all this, signal. Like if you have a U1 symmetry, you can have a strings. If you have like Z2 symmetry in the potential, you can have domain walls, and you can also have scalar induced gravitational waves, fast order phase transition, whatever you want. So in this presentation, I would like to show you some cosmic string and induced gravitational wave stuff. Okay, so sorry. Okay, so this temperature is around 100 MeV. Which is related to 10 to the minus 9 Hz or something like that. And this is 10 to the 10 GeV, which is related to F equals to 200 Hz. Yeah.
So 100 MeV or what, the phase transition?
For phase transition.
Scale in the
Now, so this temperature are quoted in general with respect to the fast order phase transition. And when I say this frequency equals to 10 to the minus 9, if the phase transition happens around 100 MeV, then you get a peak frequency at 10 to the minus 9. Some fast order phase transition with some. No, I'm not talking about standard model, like some extended stuff.
No,
I mean, yeah. So I'm talking about, say for example,
it could be. No, you can see it in gravitational.
It's with the gravitational waves. That's the idea. I mean, for example, take like some dark cubes. I mean, generally, these phase transition people study this where you get gravitational waves, the peak frequency of the gravitational waves in the nanohertz region is generally related to dark QCD models actually. So I'm not an expert of those kind of models. But if it's a dark sector, then there is.
If it's completely dark, then no constraint at all, zero.
The domain one strings are dark objects.
Could be, but not necessarily. But so for 100 MeV, 100 MeV necessarily.
Yeah. Okay, so
Sorry, that scale is in the phi. That should be happening in the phi, which is coupled to your right hand.
it's phi, yes, yes.
Yeah, that is the scale, or not.
I'm
The first order phase transition is.
so no. Look. This first order phase junction is in phi, yes.
Is it?
It's in phi. Yeah.
Then it is not dark in this case.
No. What I'm saying, this plot, take this plot for an
So I
example.
have decoupled those two.
Yeah, exactly.
It's a generic.
It's a generic. What I'm saying that depending on how you construct your Lagrangian and give the symmetry to the Lagrangian, you can, in principle, from
I
this
guess
kind of.
one conclusion would be if you take that Lagrangian,
Mhm.
you will not get anything in the nanohertz range. Is that
No,
correct?
it's not as.
cannot have the peak.
It depends on the source actually. So if you take this Lagrangian and give this Lagrangian U1 symmetry, for example, you can have an extended spectrum like this string spectrum. So this string spectrum is passing through actually all the frequency ranges. So it depends on the symmetry or which kind
You
of.
cannot have a phase transition and 100 in certain, right?
For this model, no. For this model, no. Yeah. So I took this plot from internet. So it's not related to. I didn't generate the plot from my model actually. So what I'm trying to say, depending on the model, you can have all these kind of spectrum and sources in your theory.
Why has anything to do with heat field?
This phi is not the standard model Higgs field. This phi is a singlet field. It's like something other than the standard model Higgs.
Which breaks that up.
Yeah.
That breaks-
This, but that breaks basically leptons. Yeah, lepton numbers. Yeah.
One can construct any dark system, but what is without any constraint?
I mean, it can happen in today, right? 500.
But no, aren't there constraints like from the LHC on phi?
So it depends. It depends on So it depends on which coupling regime or which mass of the phi you are talking about. So in my theory, because I'm going to talk about very high energy scales, typically the mass of this phi would be something like 10 to the 8 GeV or something like that. Yes. So LHC constraint. I mean. So what I'm going to talk about a model called U1 B minus L. So in that case, you can also have like Z or something like that. Z prime. But typically people try to constrain those models if the mass scales are low and within the LHC limit.
It constrained beyond like 3-4 TeV. Like
I think
there's some
you.
small- it's like below maybe like 50 GeV or something, where I'm not sure about the constraints, but like above 3 TeV or something, like below 3 TeV, they're fully constrained.
So
U1 B minus L model, if you're talking.
yes, exactly. I think from LHC, yes, LHC it should be below TeV, but you can also constrain from kinetic mixing with the like other photons. So like if you consider it as like a dark photon type model, then once again, if you go beyond TeV, I think there are no constraints. Yes. So
that things.
Yeah.
Cannot then event those.
Yes. In any way, I mean, if you take like something which is 10 to the 10, 8 GeV, so typically it gets irrespective of.
At 1 TeV.
Mhm.
Is it some?
No, it is basically mass. Yes, coupling is also there. Yes.
No, if you weaken the coupling enough, there is no constraint like
constraint.
1 TeV.
Yeah,
right?
here's something
You can
like-
make it out.
Yes.
Right.
Yes.
Right.
Yes.
When the energy scale is high, this domain works and strings, they will also have their own metric, right? How do you evolve that? For example, a string will have conical singular, conical metric. So how do you evolve that? You just
How
ignore
do-
their metric, gravitational effects.
No. So I'm not sure what you. So I'm
A
talking about
string by-
tensor perturbation from
No,
cosmic
a
strings.
string by itself will curve the space time around it.
Okay.
How do you take that into?
In my case, I think I didn't study that effect. Yes.
You just record them.
Yes. Not exactly flat space. So I also need to include the expansion because the cosmology. I mean, by flat space. Sorry, I misinterpreted this. I was meaning Minkowski. Yeah, but basically, you also need to include the expansion. Almost time is up. Let me give me some minutes. Yeah, I'll finish it in 10 minutes. Yeah. So okay, so this is your Lagrangian. So what happens that once this phi have this phase transition, like typically it sits at 0 because of the thermal correction, then it comes down to its vacuum. Okay, so then it starts to oscillate. I'm going to talk about the effect of the oscillation, but simply what happens that once this, if you start from like U1 symmetry in the Lagrangian, once the phi gets its web, these right-handed neutrinos become massive, and you also form like strings-like object. Okay, so this is the standard way people studied leptogenesis with cosmic strings, like just putting in one symmetry which is motivated from God. And the typical spectrum or gravitational waves from cosmic string would look like this. Okay, so it depending on the fact that how the cosmic strings form loops and how the loop radiates in the different epochs and all these things. But the typical spectrum of gravitational wave spectrum from cosmic string is like this. You have this low frequency, upward going slope, and then it becomes a plateau. Okay, so this is the standard equation to compute gravitational waves for cosmic string. The two key parameters are the expansion parameters, so loop number density, and this loop number density is basically very sensitive to like background equation of state, which background you are in. Okay, so basic scheme for leptogenesis that whenever you generate this Majorana mass term with this phase transition, and if this has a U1 symmetry, you can also produce cosmic string, and the amplitude of this gravitational waves is basically proportional to a quantity called g mu, where mu is basically v square, or v is the vacuum expectation value of this scalar field. So because this is a gauge U1. Yes, this is gauge U1.
And which electrons are charged, right?
Yes. So that's how you break the lepton.
So they will have a coupling to some Z prime.
Yes. Yeah. But this Z prime, I mean the parameters, once again, the parameter space I'm working, the Z prime are so heavy that actually you do not have any other signature. So this same V basically generate this mass. Okay. And this is first two papers discusses like production of cosmic strings from leptogenesis models. Okay, but the problem with this model is the amplitude of the gravitational waves is sensitive only to V phi, or the symmetry breaking scale of the scalar field, not so the mass of the heavy neutrinos. And as I said or explained before, in the thermal leptogenesis scenario, the scale of the leptogenesis is basically the mass. Okay, so you need to make this spectrum sensitive to to the scale of the leptogenesis, to see the scale of the leptogenesis, imprint of the scale of the leptogenesis on the gravitational wave spectrum, only if you can make this scenario sensitive to the mass. Okay, so you need to take into account this yn coupling. So because this yn coupling is coming from this Lagrangian, so you need to construct something with this Lagrangian in a way that you affect the propagation of the gravitational waves, and you get different spectral signature for different values of yn. So then the crucial part is when there was phase transition for this scalar field, it comes down to the vacuum, it tries to oscillate. And this oscillation basically happens mostly dominantly in a quadratic potential. And you can show that if the oscillation happens in a quadratic potential, then the equation of state, what you get is basically 0. An equation of state is 0 means basically it acts as a matter. So this phi, which is giving the heavy neutrinos masses, they can also produce a matter-dominated epoch, okay, because of this oscillation. So now you have a phase transition, then you have a scale of leptogenesis, and now this phi is going to give you a matter-dominated phase, which starts at T dom and decays at T decay, but this decay should happen before BBN because otherwise you are going to spoil the Big Bang nucleosynthesis. Okay.
The energy density is dominated by the spike.
Yes. Yes.
Why would that be true? I mean,
Because the matter redshifts are a to the -3 and radiation a to the -4. Therefore, if your matter component, it will at some point it will going to dominate.
because the radiation would have by then redshifted.
Yeah. So it's going as
Radiation meaning standard model degrees.
standard model degrees of
And
freedom.
that
So it's
has
going to
been shifted and this got
yes.
boosted up.
Yes. Unless you make them decay, they are going to be ever for. I mean, therefore, you need to make
That's
this.
a function of the parameter space or what?
Yeah.
How much of energy?
Yeah. That's a function of parameter space. Yes. So, sorry. So it depends on. Okay. So the expression for. Let me write down expression for TC. In this model, TC is square root of G and V phi. So if you take it, let's say 10 to the -2, it like G is 10 to the -2, where G is gauge coupling. It will be something like 10 to the -1 times whatever V phi you have. If you take 10 to the 13, let's say 10 to the 13, then it will be 10 to the 12 GV. But the generic statement is in this model TC is super high, like 10 to the 12, 13, 14, depending on the parameters. Okay, so now what I'm going to say, going to do that the decay channel of this phi, which is giving you the matter domination, is controlled by this loop diagram. Okay, and you construct this loop diagram with the neutrino Lagrangian, which was giving neutrino masses and doing leptogenesis and all these things. So now this the decay width, which essentially determine the end of the matter domination, it's basically sensitive to Mn, right? And therefore the end of the matter domination or the start of the matter domination also get tied with the scale of leptogenesis. In this way, it makes leptogenesis sensitive to the early matter domination. Okay, so now what happens for the cosmic strings? Okay, these are some.
That's the dominant way that phi decays. Is that what you're saying?
Yeah, so there are many decay channels.
Yeah.
You need to, if you want to make the duration of the matter domination sensitive to Mn, which is the main parameter I want to track, then you need to make this channel dominant and other would be subdominant. Therefore, those channel will put constraint on the model parameter space to make it dominant.
But this need not happen.
No. I want this to make, what I'm saying, within this parameter space, you can, see the scale of leptogenesis.
So why do you make it sensitive to Mn?
The motivation is, let's say this one might be is a very well motivated model for GAT.
Yeah.
That is the first one, and the statement is within this model there is a parameter space with which you can see the scale of leptogenesis, which is Mn, with gravitational waves. And because the gravitational wave spectrum depends strongly on the equation of state, which is the matter domination in our case, and in our case I'm tying the matter domination to the scale of leptogenesis. In this way, the gravitational wave spectrum will see the leptogenesis scale. So if you don't observe that kind of signal that we are going to predict, then that's the.
But you don't have this dominant decay, but still you can have a matter dominant.
Yeah,
phase or
yes. In principle,
that will be okay.
That will be okay, but it won't be with that kind of spectrum. You won't get any information about the scale of leptogenesis.
How would you know in which case you are?
Huh?
You will just see the gravitational waves, right?
Yeah.
You
So
don't know which case you are in.
no, for sure. That's what I'm saying. That this.
Yeah.
So
how will we know that you are in a case where this is the dominant? You will just see gravitational waves, right? You will see the thing due to that oscillation.
yes.
We won't know whether because it is you're in this situation or in the other one.
No, you will not. So
You
that's
will
the crucial point. No, but if you don't observe this, then within this parameter space where the gravitational wave sensitive to this scale or whatever Mn, it will be ruled out. That's that's the
So
story.
ruling out you.
Yeah, ruling out the model.
Even for the very simple thing that I would like to ask, the signature that it provides in the omega GW versus nu God, will you be able to distinguish it? Forget about pulsar timing error. I'm just talking about anything, let's say Einstein telescope or LIGO, next LIGO or LISA or anything like that. Does it differentiate between your model and let's say scalar induced gravitational wave theoretically?
But if the spectrum is different, then it's so you are saying if I get
There's a telltale signature before even going to Srihari's comment that can you distinguish between processes? My question is even more generic. Can you distinguish between the omega GW curve expectation from your theory, whatever the process is, and scalar induced gravitational wave or many other models that are there in the
I mean, just from the frequency spectrum, because if it's, say, for example, my model has cosmic strings,
Yeah.
then it will give some cosmic string kind of spectrum, with the spectral slope is very different from scalar induced gravitational waves. But
model where the scalar amplification is happening at that particular scale corresponding to that frequency, is it?
no, what I'm saying is the following. If I get your question correctly, so my model has a prediction, for example, like this, and you are saying if I have a model, let's say this is from strings.
The x-axis is mu.
No, the
X-axis, yeah,
omega GW,
x square.
and this is the frequency.
Yeah.
So you are saying if I have a different model which produces that model should have a string. So in that model, you can reproduce this curve. No, I don't think so. Because you need to, so look, the spectrum is f to the 3. Here is f to the 0. Here is f to the -1. There is no other source.
The thing will be completed by this.
Yeah. I mean that's the point of having extended gravitational wave spectrum. I mean, with scalar induced gravitational waves, you can definitely reproduce f to the 3/2 for sure.
Yeah.
Therefore, in this frequency range, for example, this passes through PTA, there is no way to distinguish it.
Yeah.
But for scalar induced gravitational waves, what will happen? Then the scarf, in general, the UV part falls very rapidly.
Yes.
So then you don't have any signal at LISA. But for this, if you have a plateau at LISA and you also have f to the 3 at PTA, so you need to do a multi-frequency detector study.
And what is the range of this particular frequency band that you are saying that from the rise to the fall?
For strings?
Yeah.
It depends on the scale. Let me. Where is it? Okay. Yeah, sure. So if you form strings with a phase transition, which is of the order of 10 to the 15 GeV, say for example, this is PTA, which is 10 to the -9 Hertz. This is LISA, which is 10 to the -3. This is LIGO, which is 10 to the 2, for example. If you take a 15 GeV phase transition, you can cover the entire spectrum. If you take, and the cosmic string spectrum goes like this. This is for 10 to the 15 GeV. Okay.
Will be very difficult.
No, it's from GART models. You can GART symmetry breaking chains are like this. Once again, it depends on the inflation model. So it's really reheating is not a generic statement. Yeah.
Yeah, I got the
Yeah,
answer. You're saying that it is 10/15, then it is like.
And basically, if you lower the scale, then the spectrum decreases like this. I mean, it still can have extended spectrum, but the overall amplitude decays in a way that only if you have 10 to the 9 GeV breaking, it will be sensitive to some daisy go. Otherwise, it doesn't go.
New scalars and
Yes.
so that decay from that the tree level decay is also possible.
Yes, exactly. So that's the point. I think that also related to Shreyari's question. So what I'm saying, the decay channel is phi is going to standard model X, and with the same tree level decay, you can have a decay channel like this. Okay. So what we assumed that this guy dominate the tree level decay. So you basically generate the portal with loop. Not zero. So typical to have a matter domination with this kind of coupling, like loop generated coupling, you need to have the tree level interaction, which is of the order of 10 to the -10, less than 10 to the -10 or something like that. Yeah. So now, okay, so whenever you have an oscillating scalar field, you also need to take into account like different kind of effect like damping. So damping of scalar field itself is like different topic to discuss. But what I would like to say that for our parameter space, we do not have significant energy transfer via damping because it is also interacting with like plasma with different particles because it has coupling with neutrinos and gauge bosons and all these things. And also, whenever you have an oscillating scalar field, you can also have some production of particles with parametric resonance. Okay. So in our case, and the particle production occupation probability is defined by this parameter. So if the daughter parameters, daughter masses are like light, you can have significant amount of particle production that can drain the energy from the scalar field. Therefore, you will have less matter domination or less possibility of matter domination. In our case, we are in the super heavy daughter regime of this particle production, in which case the particle production is suppressed by a factor called Landau-Giner factor. So we are also free from this. So look, I just got to know about not particle production, but in damping in general after the referee report came, because we did not include damping first, and they complained a lot of things about this non-inclusion of this damping in our scenario. But in our scenario, damping is not significant. So whenever you have a matter domination like this, so you get an like bending of the spectrum, and within that parameter space where you get the bending, it will depend on which kind of mask you choose. Okay, so in which case. So this is the typical parameter space and all this thing. What I would like to tell you that this is the main plot of this scenario, that if you have like choose a different mass scale, you will have different plateau and different this break frequency depending on the masses. For example, already some region is excluded by PTA, and if you don't observe this yellow region, that means within that parameter space you cannot have leptogenesis at the scale of 10 to the 10 and all these things. Okay, so within the same model, because we have this early matter domination, you can also produce an induced gravitational waves, as Dheeraj was talking about. Okay, so this plot is scanning all the taking this plot is generated taking into account that our gauge coupling is a free parameter. But if you increase the gauge coupling, actually when you are at the tip of this parameter space, basically the gauge coupling values are quite large. So typically you can map it to different GART scenarios, and in which case the mapping is very sharp. Like if you are at the tip of this parameter space, then basically there's the mapping of scale of Leptogenesis to the spectral break frequency is almost 1-to-1 for GART-based models. Okay, so okay, 3 minutes. Okay, so in this model, you can also generate induced gravitational waves. So whatever people studied induced gravitational waves in the linear regime, and recently there is a loss of interest of non-linear regime, studying the non-linear regime of induced gravitational waves, which you can produce. Whenever you have matter domination, you basically increase the density perturbations, and whenever this spectrum for density perturbation goes more than 1, you are in the non-linear regime, and production of gravitational waves through these early structure formations in the early universe is quite abundant. For example, this was studied so far, but now the new studies, this is a result from the recent lattice and body simulation. So you have almost 4th order of magnitude enhancement of the induced gravitational waves in the nonlinear region. And in our model, it's very easy to produce these gravitational waves as well. Okay, so I would like to. This is a typical spectrum that we will get in our model, depending on the mass of the neutrinos, due to the amplification of density perturbation because of the matter domination. Yeah. Okay, so once again, you can have a 1-to-1 correspondence with peak frequencies with the scale of leptogenesis, and therefore, if you do not observe this island of parameter space, your model will be rolled out. So this is we did a little bit of parameter reconstruction. For example, this is for LISA. Sorry, this is for LIGO or ET frequency. And if you fit the peak frequencies at the ET telescope band, then you will get this parameter space, which basically corresponds to very high scale leptogenesis. And whenever you come to the left side or lower the frequency regime, is basically your scale of leptogenesis basically decreases, and in the PTA regime, you can fit the PTA data with intermediate scale of leptogenesis. But whenever you try to fit the PTA data, the mapping is not that sharp. We have lots of degenerate parameter space, but still it's quite good that in this model you can fit 10 to the 5 to 7 GeV neutrino mass to PTA data. Okay, so this would be my conclusion, that simple models of leptogenesis have all the ingredients to produce early matter dominations, and whenever you have early matter domination, if you have a gravitational wave source, that will leave a very distinct imprint on the spectrum. And gut motivated model have like nice U1 symmetry. You can study strings and all these things. And in this work, I kind of tried to explain that simple model of leptogenesis, you can have this early matter domination, and I basically discussed two spectrums, strings and early structures. And of course, non-observation of such background would rule significant amount of parameter space, which were not touched at all. Okay, so what I would like to mention at the conclusion, that this was a particular model, and you can do the similar stuff. For example, so I discussed strings and scalar induced gravitational waves, but you can do similar stuff for many BSM models, including dark matter. I mean, lots of people are working on that. Dark matter, axioms, leptoquark, whatever you want, and mainly so far this field has developed, I would say, semi-analytically. There are lots of scopes to do numerical simulations, which I'm working on, and therefore because lots of detectors like LISA will get launched in 2030. For example, Einstein telescopes is ready, so it's a very good time to do this kind of physics. Of course, there will be degeneracies, lots of degeneracies in this kind of study, as we already discussed, that you can reproduce the same spectrum with many models. But still, this is good, because if you don't observe the spectrum, that is the main point of my talk, you can rule out many models with gravitational waves experiments, and even with the pulsars, which is a purely astrophysical stuff, not anything manual, just excluding parameter space, high energy physics parameter space with pulsars. I think it's good. It is quite incredible, and some people are already giving talk with the title that we are already in the pulsar timing frontier of high energy physics and cosmology. So you are invited to work and collaborate. Thank you very much for your kind attention.